In 7.4, we're going to focus on a third transformation called a translation. That's like a slide. Um, in a translation is an isometry. Okay, this is like a slide. It is an isometry, which means length is preserved. Okay, so all points slide the same direction and distance. So for example, you can slide this is my pre-image, here's my final image. All my points slid the same way, same direction, and same length. These are the length are all the same. Um, like the double reflection before, where in the last theorem, um, reflecting over two lines that intersect, we doubled the angle of that intersection to figure out the angle of rotation. Well, if we reflect over lines that are parallel, what happens is, what we're going to do is we're going to double, we're doubling the length. So if this length is, let's call this length x, this length is going to be 2x. Okay, or here, I guess I have something already. If this is d, this length is going to be 2d. From here all the way to there is 2d. And it makes sense if you think about it, because this length and this length are the same. This length is this length, and then this green length and this green length are the same. So really, from in here, we have half the blue, half the green. So it makes sense that the total length is going to be double. But a double reflection is the same thing as a translation. Here's a picture. We got some things labeled, and this is basically all this is saying. Triangle XYZ is getting mapped to triangle X prime, Y prime, Z prime by a double, doing a reflection and then reflecting that resulting image to get a new image. And we're going to be asked some questions like name some congruent segments, what a blah blah blah. Well, basically what we're trying to get at is, we know that this length and this length have to be the same, so this has to be 3. This length and this length have to be the same, so that has to be 2. We don't know, we know this length and this length are congruent, but we don't necessarily know their lengths. We know the total length from here to here is going to be 6 plus 4. This total length from y to y double prime would be 10. We know different things like that. And we know that these segments are perpendicular to each other because it is a reflection. Sketch the image after a translation, and here is more coordinate notation. And we're going to talk about a different notation we can use to describe vectors soon, so make sure you know the name coordinate. We're using coordinates to describe the translation. So -4, -1, that's R, -2, 0, S, and -1, 3, T, -3, 2. All right, so we have this. Looks like a parallelogram. We want to translate by this coordinate notation. So we're taking a point x, y, and we're going to add 4 to the x coordinate and subtract 2 from the y coordinate. So if we look at R, the point -4, -1, we are going to be adding 4 to the x-coordinate, and we're going to be subtracting 2 from the y-coordinate. So we would get 0, -3. So this would be r prime. 0, -3. And if you look at this, this might make sense. So my x-coordinates, we're moving 4 in the x-coordinate direction, and we're moving 2 in the y-coordinate direction. So we're going right 4, down 2. Okay, and you can find that by adding 4. So then, s, -2, 0, that's going to get mapped to s prime, which is add 4 to -2, and subtract 2 from 0, 2, -2. This is going to be s prime, and notice the pattern, we're going over 4, down 2. Over 4, down 2. And you can kind of, once you get the pattern, it can help you. I have a lot of blue lines in here, but this will be t prime and u prime. Notice it is an isometry. Those shapes are still congruent. Now, vectors are actually very important for higher level mathematics and science. You use them all the time in physics. But a vector has a magnitude and direction. So magnitude is how far it's going. It's going this far and in this direction, okay, in the direction of this arrow. The initial point is kind of like the same thing for a ray. Initial point is the start. Terminal point is the end, and that has to be the tip of the arrow. Okay, this is a little bit different than a ray. A ray would keep going, but this arrow means it's stopping here. Okay, it stops, it terminates. It's not a ray, and we're going to use a symbolic notation of this. It's this little almost half arrow is the vector notation. So this would be vector PQ. And just like a ray, this is the initial point. And this is the terminal point. Okay, you always start with your initial point first, and go towards the one that has the arrow, the terminal point. Now we can write a vector in component form, which uses these angled brackets, and we can say how far they're going. So this would, vector PQ would have a component form. We went 5 units in the x direction and 3 units in the y direction. Best way to describe it, component form, is just to look at this example. Over 5 to the right, up 3. So in the diagram, name each vector and write its component form. This would be the vector CD, and I put the half arrow over the top. And notice it started at C, tip of D. I went down 3 over 1. So down 3 over 1. This would be the vector EF. And component form would be over 4 up to 0. And the last one, hopefully you don't mind if I switch this on you. I want one that goes the other direction. Something more like that. Okay, so be careful if you have one that's, this is still my initial point. So this would be vector HG, how I changed it, where the arrow's over here. That's my terminal point. And I'm going -5, -2. Okay, how it was, it would have been different, right? So I changed it. All I did was I flipped the arrow, the end of the arrow, but that changes how you name it, and it changes the component form. Okay, notice the component form is different than the coordinate notation. The component form of vector RS is 2, -3, to the right 2, down 3. Use that to translate the quadrilateral who has those vertices. So if I go to the right 2, G prime is going to be at -1, 2. I went from 5 down 3. Okay, so G prime ends up there. Notice I'm basically adding these two things together. So I get 2, 0 would be H prime. Add this and that, 3, 0 would be J prime. And that should have been written over here. As it turns out, you never really know until you start drawing them. And I got one more point. 5, -5. 5, -5. 1, 2, 3, 4, 5. An ugly looking quadrilateral, but unless I plotted a point wrong, nothing wrong with a quadrilateral that looks like that, but it's not typical. Wouldn't be surprised though if something did go wrong when I did something, but and I think we're getting there. Write the component form of the vector in coordinate notation that can be used to describe the translation. So coordinate notation, that's the x, y, it's mapped to x something, y something, and the component form is where we use a vector. Okay, so this is the vector coordinate. We want to use coordinates, an xy coordinate. All right, so identify, here is my pre-image. It's important to find that. Here's my pre-image, so I'm going this way. It's green. I'm going this way. So I went backwards 3, 4, 5, 6, 7. So I went backwards 7 and up 3. Backwards 7, up 3. Component forms -7, 3. And that means, what am I doing to my coordinates? Well, I had to subtract 7 from my x coordinates and add 3 to my y coordinate to move it up. So, component form, coordinate notation. Okay, two different ways to describe the same translation. I'm going to skip this problem. There's a look at your homework. Not too bad. Graph paper is definitely useful. You can get that in class. See you then.